that's a safety note. When you're doing this, occasionally check the string to make sure it's not about to break. We'll do a 200. All right, so if I just let go, unless there's enough friction there, this should fall and this should rise. However, if I swing this, there's an ideal speed in which this is not going to move up or down. Now, if I look at that, it'd be difficult to tell if it really moves up or down, so I'm looking at this piece of tape right here. Too far. Trying to get a stable swing here. The string is marked to where the bottom of the tube should be. And so what we're trying to do is figure out how fast does that need to be going in order for this mass to be in equilibrium. So we have, this is equilibrium. Except it looks more complicated because we now have an angle in here. This length right here is L, technically to the center of mass. And what do we make this? 0.7 meters. Mass of B, we're going to make 0.05 kilograms. And the mass of A, we will make 0.20 kilograms. And actually, we'll be more specific here. A is in static equilibrium. Because you can be moving and be in equilibrium.
That just means like your velocity is constant and your acceleration is 0.
That's equilibrium, yes. Static means and not moving.
So when we were doing our K equations, that was assuming an equilibrium.
The K equations assume that acceleration is constant.
Oh, not 0, right?
Not 0. The jerk is 0.
So to be at equilibrium, but not while moving, you need constant speed but 0 acceleration.
If it's moving at a constant velocity, not just speed, but constant velocity, then acceleration is 0. That's dynamic equilibrium. Now, from a problem-solving point of view, if it's in dynamic equilibrium, you don't have to worry about is it moving or not. If there's friction involved, you're using kinetic.
Why did I say that's absolutely wrong?
Okay, art school. My mom actually had a real talent for drawing, and it skipped a generation with me. All right, we've done it so many times before. Let's start out with
Tension. On. And then on B.
And then weight is down on it.
probably the 0 should be the same length, but that's weight A. Weight of B. Which way is the tension going on B?
This one.
Good. All right, so which of these angles is theta? Is this one to the horizontal theta or is the one to the vertical theta?
We have to take the, oh wait, no, it's to the horizontal.
Yeah, it is the horizontal, so that one's theta.
Can you explain that real fast? Why is it the horizontal one?
If I'm looking at this diagram right here, that's my horizontal.
Okay.
I know tension is along this line right here, and so two parallel lines cut by a transverse alternate interior angles. Congruent.
Oh, I was thinking like, it looks.
And actually, That's legitimate also, as long as you don't draw it at a 45-degree angle. The faster you spin it, the smaller theta is gonna get. All right, so we did that. Now what?
Acceleration.
Okay. So what's the direction of acceleration of A?
Oh.
All right, what is it for A?
Zero.
Zero.
Okay. And for B, Scott, you were answering that one?
We go to the left.
That is correct. Probably one of the biggest mistakes, and it shows up more in another problem, the car on a banked curve. But the acceleration is that way. It is not that way. It is towards the center of the circle. That's why I drew the dotted line right there. So my acceleration is in that direction.
All of this means we're gonna have to decompose.
Yes, it does. All right, coordinate system, coordinate axes.
Let's pick a left line. And Jan.
Y is up, J hat.
That is listed.
What, sorry?
I think listed.
Go. No, it's up because I think I agree with that because you said so.
We do down.
Okay. And as a general rule, if you sort of follow the string, if my acceleration is positive going to the left here, the string just then comes down. And so this is probably the preferred way of doing it, although it will not matter mathematically. Okay. What now? We have a coordinate axes.
Decomposition. Okay.
What are we breaking up?
Tension.
I think somebody said it.
Tension?
Okay, I heard tension. Maybe I'm just feeling it. All right, so WB is right there. So we have tension being broken up. Which one's which?
So you're,
Would the bottom one be cosine?
I would agree. Bottom line is cosine.
Is it time to stand up and say, Skylar, Ibrahim, what were you thinking? Anyone else agree with him?
is your hand when you said no?
Well, no one wants to question your thinking, but no one wants to back you up, so. This is whatever I'm breaking up is my hypotenuse. I'm breaking up into horizontal and vertical. This angle here is theta, my hypotenuse is tension. And the adjacent one is indeed cosine. This one would be sine. So they were correct. Ft cosine theta, Ft sine theta. We don't have to break up the other one, so we are now left with, what's next after decomposition?
Equation.
Question or you button?
I did have a question. We don't break up the weight because it's not, why don't we break the weight?
You need to break up things that are not immediately in the I hat or negative I hat direction, J hat or negative J hat. J hat is up, weight is down, they're anti-parallel, so I can express it completely in negative J hat direction. Other questions? Or someone dazzles me with the equations of motion? All right, I'm prepared to be dazzled.
We have three.
Yes,
I had B. Would be ft cosine theta minus, no, equals, m sub, b, a sub b.
Yeah, no harm in that.
J hat. That is,
Oh, I guess I just have an I hat and J hat, so I don't need those others there.
FT sine theta minus weight B, or that would be equals M subscript B.
Like you mean it.
0.
There you go. Yeah, if it were accelerating in the vertical direction, that means the velocity is changing, which means that it'll be moving up and down. And as you saw earlier, I did a perfectly horizontal circle. And you can always check the video afterwards. Any deviation from the perfectly horizontal circle, obviously, the camera's got issues.
The last one would just be plus, like we did in the other one.
It would be what?
We wrote it just as a plus last time for
Yeah.
A. It would be ft.
Let's stick with the convention.
Oh, weight. Minus ft equals ma, or m subscript a. 0.
All right. So we got our equations of motion. I'm sure we're all feeling a little bit buzzed here. Let's try to, what do we do next? What are we gonna substitute?
The mass, the acceleration.
Weight, acceleration.
Yes, weight and acceleration.
Oh, you know what?
I guess you could do a mass substitution and solve for weight, but, you know, hey, whatever your thing is. So I have ft cosine theta equals mass of B times,
V squared over R. And will direction always be implied? Like
for each of these. I mean, the directions implied here, these are all J hat.
right, but so, okay, so like with that in mind, like each one of these equations, because that's part of the facades part, we don't have to really worry about the negative R now.
Correct.
So we
Yeah,
just-
if you're doing it right, you don't have to.
Okay, so the only thing that is of any concern to us when it comes to using that equation is the V squared over R.
Right, and conceptually knowing that it's towards the center of the circle.
Right, okay.
So ft sine theta is equal to mbg, and mag equals the tension. And we're trying to find V. Well, actually, we do have one other substitution. Well, no, it's not specific to this one, never mind. Let's think about what our unknowns are. We don't know tension, although we could find it. We don't know theta. We don't know R. We don't know V.
So 3 unknowns.
Oh, no.
I have a question.
Yes.
We might have not gotten to the part of it, but where does L fit in?
That is an excellent question.
Is that R?
No.
Would it be, is L supposed to be like the diameter? No.
What is L?
That's the distance
From,
from the center.
my sense of orientation is way off there. which is the direction of the center.
Oh, the distance from.
L is that direction. R is that direction. R is. That's R. What is the relationship between L and R?
They equal.
L is the hypotenuse. I mean, it's a physical triangle. So I've got hypotenuse of L. This angle here is theta, and that is R. What's the relationship between R and L?
Cosine? Would it be cosine?
L cosine theta. So now, we have another equation that we can do a substitution right there. I'm going to erase this for space. Anybody need these equations? So I have tension times the cosine of theta equals mb v squared over L cosine theta. I have tension times the sine of theta is mbg, and mag is equal to the tension. All right, now I'm down to three equations, three unknowns.
So we can put in MAG into the second equation.
Okay. Into the second equation. All right, so I got MAG sine theta equals MBG.
I would say you could also put it into the first equation.
Okay. MAG cosine theta is equal to MB v squared over L cosine theta. It's lovely having a cosine theta in the numerator over there and denominator over here. Good times.
Would you cancel those two out?
No, you can't. Across an equal sign, they have to be on the both top or both bottom.
Wait, can you say that one more time?
I can't cancel those cosines out. Because if I, cross multiply, the cosines aren't gonna cancel, are suddenly on the same side. Across an equal sign, I can't cancel them out if they are diagonal.
So from there, do we, is that as much substituting as we can do?
It depends upon how convoluted you want your final equation to be. You're making a push for putting in numbers?
Yeah, I don't think we need to substitute.
We can do one more simplification.
Multiply on that side, MB over cosine theta by each side.
Wait, get the.
Yeah, to separate the.
Oh, get VL by itself?
Yes. I mean, yes.
So v squared equals MAGL cosine squared theta. That work better?
Yes.
Down here, we can simplify it one step further.
Cancel the G's.
Yeah. So I have MA sine theta equals MB. It is solvable solving for V. It's not too complex. There's a different way of approach that we'll do after this, but.
When you simplify that one, the MAG cosine theta equals MVV squared.
Oh, MAG cosine. This one.
Where did the
big equations of v squared, could you put the MB in,
Oh, put that in here?
or does that just make it more complicated?
You could, that actually is gonna make it more complicated. But I'll be glad to do it if we wanna go that route. I think Jack's suggestion, might be the wiser course at this point.
Is there a point where we would know if we just added more equations in, it would be harder to solve, or do we kind of just figure that out?
Wait, sorry, make sure, ask it again, make sure I answer the right question.
So is there a point, like with an equation, that we can tell that's like the simplest form that we, or like the easiest form to figure out?
Not always.
Okay.
That would be nice, but if we plug in numbers, we know MA and MB. So we can find sine theta. Once we have that, we have theta, we can plug theta into here.